integrated circuit designing is a time and effort-intensive process. Journey of a chip starts with specification and reach to the point of tape-out through some steps. All steps are very much well-defined and well-connected and in sync with the adjacent steps. With time, technology has moved forward and feature size of transistor has reduced, although the basic structure of IC design methodology remains same over time. With time, new substeps have been added to handle the challenges. In today's episode, we will discuss the methodology of IC designing and importance of Y chart in it. If you are interested, stay tuned till the end of the video. So let's see the pointer we will cover in today's video. First, digital design, then hierarchical design approach, next design hierarchies, next Y diagram, then domain and levels, then mapping of levels and domain, next regularity, modularity and locality, next design development, and finally design stages. So let's move to the first slide, digital design. Well, designer starts with a set of initial spec. Most often, such spec is incomplete and even inaccurate sometimes. Designer makes a number of design decisions both in terms of logic design and physical design. In the meantime, he also modifies or refines the specifications until a final design is reached. We use this diagram to make it more understandable what we are saying. It starts with initial spec and then there are 3 pointers. The structure is like a triangle, modification of specification or the spec, and then physical design decisions and logic design decisions. There are 3 points and as we can see, they are connected with bidirectional arrows. So if we need to do any kind of modification in spec, so accordingly we have to change either logic design decisions or physical design decisions or vice versa. Like if there is needed to meet the design demand, if we need to do some or take some physical design decisions, accordingly we need to modify the specification. So finally with many iterations we will reach to a point where the design is finalized, so we will get the final design. The hierarchy approach divides a module into submodules and then repeat this process on the submodules till we reach manageable smaller parts. There are 2 approaches, top-down design and bottom-up design. Design process is a combination of top-down and bottom-up processes that are happening concurrently in the designer's mind until he reaches a final correct design. Usually, IC design process follow a hierarchical approach. First, the initial spec or behavioral idea that how the system we want to design it will work, how it will behave, what is its intended behavior, because obviously our design has some purpose. There is no design with zero purpose. Obviously they have some purpose, they must do some work, and to do that work, how it can be achieved, that's the goal. So this way we define the more finer parts or more detailed work methodology of the system. So first, its hierarchical approach is followed here, and a bigger module is subdivided into some submodules, and again each submodule are similar way divided into smaller modules. This model is repeated until we reach a manageable smaller parts. And this hierarchical design method has 2 approaches, at top down or bottom up. Now let's move to the next slide. Hierarchical design approaches. As we said, top-down design, top-level block is designed first and then comes to the sub-blocks. Further, the sub-blocks are subdivided until the procedure reach leaf cells. Initial design steps are quite abstract and theoretical, and there is no real connection with silicon. Top-down design methodology starts with the bigger block in hand. First, the top-level block or the bigger block is, or biggest module is designed. Then, according how it should work or its purpose, according to its purpose, it's subdivided in some sub-blocks, as we have shown here, that sub-block 1, sub-block 2. There are 4 sub-blocks, and again those are divided some smaller blocks, and then finally we reach to a point where there is leaf cell, the smallest part or smallest unit, that is leaf cell. It's basically divide and conquer approach. Next, bottom up. methodology, that is bottom-up design, starts at the silicon or circuit level and builds units like logic gates, adders, and register as the first step. Then gradually group them up to build modules, and finally the whole design is completed. It's just the opposite of this top-down design methodology. We start from leaf cell designing, or we start with leaf cell from library, and then with that we design logic gates, adders, and registers, and then group them according to their work or purpose, and then gradually another module, bigger module, and finally we reach to the top level block. So next, design hierarchies. There are three major design hierarchies: behavioral hierarchy, structural hierarchy, and physical hierarchy. The mapping of behavior into structural hierarchy is logic design process. First, let's try to understand that what is that behavioral, structural, physical hierarchy. When we design a system, there are three aspects of it. When we design a system, we must understand its purpose. There is no system design which is zero purpose. First thing which comes into mind, that it's behavior. We are going to design a system, it will do this and that work. Then we have to think, if it's going to do this and that work, then how it can be achieved, what will be its structural components. Then we have to think how it should be on physical world. Silicon based chips covers the major portion of all VLSI chips and all. So how it work on physical silicon. So that's the physical part, because it must be a realizable design in terms of silicon, physical silicon. Here comes the importance of physical hierarchy. So when we map this behavior into a structural hierarchy, that is called logic design process. And when we map that structure into physical hierarchy or in physical domain or aspect, it's physical design process. It means from behavioral, we are getting that design into some subunit. That part is logic design, and from that it's designed on physical silicon, or it's ready to be designed on physical silicon. That part is physical design process. Behavioral and structural design processes go on concurrently. Mostly these are top-down approaches, and while physical design process is done separately, and usually physical design process is done by bottom-up approach. Physical design leads to iterations in behavioral structural hierarchies during a design. In fact, physical design is probably the most important part of, and also the most complex part of VLSI design, because when we are thinking physical design, it's about realistic world. It should not fail on silicon. It should not fail on the customer end. Ultimately, we have to work with some chemicals, some materials. They have some chemical limitation. They have some physical limitation, or their structural atomic level limitations. So not everything is possible to fabricate on silicon. From there so many substeps arise. As we move to smaller feature sizes, substeps arise because of those physical limitations and defects. So we have to keep that also in mind. Next, this hierarchical behavior design process provides for a iterative refinement of the initial design specification. In the very first slide, we showed a triangle-like structure that actually says that we said in the very first slide. Now let's move to the next slide. Y diagram. Well, this is a Y diagram. Behavioral, structural, and physical domain. We can plot their substeps on a single diagram. Help us understand digital hardware design. These three axes represent three domains. And behavioral domain is what a particular system does. Then comes the structural part, how entities are connected together to get a system which will work according to that what we have already fixed. And behavioral domain, there must be some submodules and how they are connected so that the whole system works according to our plan. That's structural domain is all about that. And finally, physical domain, how to build a structure on silicon that has the required connectivity to implement the behavior. As we can see, there are 5 concentric circles represent 5 levels of importance or details or level of abstraction in the design. If we move from outside to the innermost circle, it's system level, then algorithm, then register transfer level, then logic level, then circuit level. outermost circle is the most general, and each circle closer to the center represent a smaller and more specific part of the design. And the 5 main characteristics at each level of abstraction are basic building blocks: signal representation, time representation, behavioral representation, and physical representation. The system level, the outermost circle, represent the system level. If we move to behavioral domain, it's represented by system specification. And if we move to structural domain, so it's saying about CPU, memory, IO. And if we move to the physical domain, it talks about the chip, physical partitioning. At the same time, in the next level, algorithmic level, it says behavioral domain, it's about the algorithm. And in structural domain, it's about subsystems, FSM, data path. Definition become more specific if we move from this point to this point. The more detail about the system is revealed. Obviously, a behavior of a circuit is defined by its IV characteristics, transfer functions. So here transfer functions are in behavioral domain, it's transfer functions. Structural domain, the transistors, its parameters. And obviously, when a transistor is fabricated on silicon, it's transistor layout. Whatever diagram or cross-sectional diagram we see in our books, that's for our understanding. But when it's on silicon, it's about layout. So let's move to the next slide. Domains and levels. Now, with a diagram, we try to show different, like first it's system, then system is built with different modules, and then a module, if we subdivide it more, then comes gates, and gates are realized with circuit is built with devices. So behavioral domain is all about how a system functions. We imagine a part of the design as mysterious black box and focus on the relationship between inputs and outputs. In structural domain, we describe a system by its different parts or subsystems. And in geometrical or physical domain, gives information on how the subparts can be seen in structural domain. Level of abstraction could be defined as the amount of information that level is hiding within it. Higher level of abstraction means less detailed a level is, so more information is hidden. Lower level of abstraction means more detailed a level is, so less information is hidden. System or processor level is highest level of abstraction. Switch or transistor or circuit level or device level, that's the innermost level of abstraction. Now, mapping of levels and domains. So there is a table, system or processor level. In behavioral domain, what we do, that written specs. In structural domain, modules and their interconnection is defined. And physical level, partitioning. Next, chip or algorithm or architectural level. In behavioral mode, we decide how that sub-modules will work, like algorithms, flowcharts, these are defined. And then processor, RAM, ROM, there. So from modules, we go more detailing, and it's the level of abstraction we get reduced, and we now define that RAM and ROM and other processor and other units which will be used to realize that behavior. And physical domain, we talk about clusters. Then functional or RTL level, data flow, register transfer, that's defined in the behavioral domain. And structural domain, ALU, marks, register, counter, which are used. So more detailing. And physical domain, floor planning, standard cell, and then get structural logic or logic level, that is defined by Boolean equation. And then design domain, it's AND, or flip-flops, etc. We defined by this. These are required to realize these Boolean equations and all of. And then cell, module, plans, these are defined here. And at final, switch, transistor, circuit. This is the lowest level of abstraction, that is switch, transistor, circuit. So at that level, behavior is defined by differential and transfer equations. How voltage and current related. Now transistor, resistor and capacitor. At structural level, obviously transistor, resistor and capacitor. How at ground level the circuit works. It's all about that in structural level. And to realize that, and physical level, what we need, mask geometry. So we can basically map these are not disconnected things, these domains and levels. So next, regularity, modularity and locality. Hierarchical design approach reduce the design complexity by dividing the large system into several submodules. Such decomposition of a large system results in simple and similar blocks. This is called regularity. If the whole design can be designed with similar blocks, then mass process become very easy. And when chip is designed in mass process, its expense of fabrication or designing become less. So regularity is really helpful to not only to reduce the design complexity but also in terms of money. Functional blocks which make up the largest system must have well-defined functions and interfaces. This is called modularity. And modularity allows that each block or module can be designed relatively independently from each other. They have every functional block has well-defined functions and interfaces. We know where to place them. They are not dependent on other module or other blocks. So that independence is important, that we can place it where it required. It's not that we use a module, we need to use another module which is not that required. So every module should be well defined with their functions and interfaces. All of the blocks can be combined with S at the end of design process to form large system. All the blocks or modules, they must be complete in their own identity, and then they can work together to form a larger system. That's the thing. The concept of modularity enables the parallelization of design process. Locality is ensuring that connections are mostly between neighboring modules, avoiding long distance connections as much as possible. Long distance connection is always avoided because of system latency and loss. So more the connection, loss will be greater. So it's always good that connections are local. Then data transmission is more flawless. Next, design development. It's a Y diagram basically in a different way. We will understand how design is developed with the help of Y diagram. So design flow starts from algorithm describing the behavior of the target chip. Corresponding architecture of the processor is first defined and mapped onto the chip surface by floor planning. And next, in behavioral domain, finite state machine FSMs are defined and structurally implemented with functional modules such as registers and arithmetic logic unit. This algorithm and subsystems are defined, and then we define their algorithm. ALU and register and marks are defined. Next, we move to this register transfer. This ALU, register and marks, their equations must be, or their behavior must be defined by this register transfer description. And then we go to lower level of abstraction and define the gate and flip-flops. Then we move to their logic expressions. Then we finally move to transistor. And obviously, when we are at transistor level, their behavior is defined with transfer functions. And these modules are then geometrically placed onto the chip surface using CAD tools for automatic module placement, followed by routing with minimum possible interconnects and signal delays. These are the concern at physical level which are addressed by CAD tools. And this is basically the physical design part. These are the concerns or the main thing we do at physical design level, that CAD tools are used for automatic module placement and with minimum possible interconnect. The lesser the interconnection length, loss is less. And next, behavioral description of modules are defined and implemented with leaves. So behavioral description, we have to get it by leaf cells. Their collective behavior must build up in such a way that we get the final design. Now let's move to the next point. At this stage, the chip is described in terms of logic gates or leaf cells. Leaf cells are placed and interconnected by using a cell placement routing program. At the last level, detailed Boolean description of leaf cells are followed by a transistor level implementation of leaf cell. Finally, mask for the design is generated. In standard cell-based design, pre-designed cells from library are used for logic design. The design will be transferred on the silicon using that final mask. And that design already at software level, it has met the power, area, timing, constraint, everything. As we can see that behavioral domain and structural domain, top-down approach is here followed. Bottom-up approach is followed in physical domain. Usually it's mix of both. With iterations, we reach at the final design. Now design stages. It starts with specification. So we design steps grouped in different categories. First, logic design written in C or behavioral, HDL or Verilog. Then comes simulation. Functional simulation is to verify the behavior and compliance with the spec. Next, synthesis. Hardware description is converted into lower level description, that is logic or Boolean expression. Some of the main steps are high level synthesis, register transfer level synthesis, gate level synthesis and technology mapping. So by synthesis, we get the gate level netlist and then we enter the physical design. Next, Verification, it's checking whether a design meets the specification and performance parameters. Three main ways to check the correctness of IC without fabricating. It includes prototyping, simulation, and formal verification. And final, testing. Checking is done to see whether the device is properly fabricated or not and detecting the physical defects of a die or package during manufacturing process. There are errors. To minimize the error and to detect it, there are testing processes. With testing, we are saying about that. And some of the design tasks are clearly visualized as transition in Y chart, either within a single domain or from one domain to another. That's all we had for today. Thank you very much for watching up to this point. Please share, comment and subscribe. In case you have any question, query or dislike, put it as comment. Thank you and bye for today.